And we're back into question number 3 from our practice exam. So I'm working with these alloys, and now I'm trying to fill out these deformation mechanism maps. So I know the dashed line represents my theoretical stress, or theoretical yield stress, TS, they're all at 0.1, because we know that theoretical yield stress is usually going to be about, so my Y theory is going to be typically on the order of basically my, either E divided by 10 or my Young's modulus divided by 10, or my shear modulus, divided by 10. So those are my theoretical yield stress. The next one will be my dislocation glide. So again, high, very, very high stresses, and then basically for all temperatures. Elastic, low stresses, low temperatures. And then now we have to kind of think about these things. So we know when does Coble creep dominate? So actually, we know that power law dislocation, so PLC, is always going to be this highest regime here because that scales as PLC. So if we go back and look at our notes, remember, we're always looking at kind of this key expression and actually the scaling relationships for these different, the scaling relationships for these different creep mechanisms. So we always want to basically be able to, and actually to write on our exam, what are those scaling relationships, and then how can we use that to kind of determine what's going on for creep. And remember, creep is insidious because at high temperatures, our material is going to yield at lower yield strengths or lower yield values than we kind of initially and previously thought. So our kind of general expression is always as follows. So my strain rate of creep is equal to, basically, there's going to be a couple of constants that we'll introduce here. But in our most general equation, I'm going to have some constant, here we go, K, some creep mechanism, stress to the X power, my dG to the Y power, and then some type of diffusivity C here. So when we're looking at our different types of creep mechanisms, we know that for Nabarro-Herring and for Coble creep and for power law creep or dislocation creep. So if I go to this, if I look at my, basically, what is my, kind of diffusion, what is this kind of C value or activation energy here? What's my Q? Because again, remember, D is equal to D naught exponential, minus Q over KT. And again, we could be diffusing along, if we look at a material with certain grain size, we could diffuse essentially along the bulk or within the bulk, or we could diffuse along these grain boundaries here. So diffusion along the grain boundary is always faster than diffusion in the bulk. So for Nabarro-Herring, we're looking at basically our bulk or our kind of lattice diffusion, same thing for DLC. For our X, that's our stress. This is also 1 and 1. For Coble creep, we're in the grain boundary, so B here. And then finally for Y, how does it scale with my DG, my grain size, is going to be the -2 here, -3 here, and then for PLC or DLC, 4 to the 6. So huge emphasis on the stress there, and then this will be to the 0. So DLC, PLC will be at the top here. My Coble creep, it dominates at very, very, very small, and I'm looking at the diffusion along the grain boundary. So for small grain sizes, basically Coble creep is going to dominate, and because it's looking at the diffusion within the grain boundary, it could occur at basically lower temperatures. So I'm going to look at this being Coble creep, this also being Coble creep, this being Coble creep, and then my other region is just NH, 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 because higher temperatures, NH. So there we go. So it must exist at higher temperatures there. So that's basically all of our plots labeled. So now we're asked to basically re-examine and look at these plots here, A2, A3, A4, A5. So if we look at it basically from 2 to 5, 2, 3, 4, 5, we know that basically our yield strength of 5 is greater than my yield strength of 4, which is greater than my yield strength of 3, which is greater than my yield strength of 2. Let's just make sure that that is indeed the case and I'm not labeling those incorrectly. Yeah, that's pretty much true. So I know, looking at this value, this value, this value, and this value right here, that gives me my yield strength. So this must be 5. And then let's see which ones. this one must be 4. This one, and you could also look at this for the size of the cobalt creep region as well. So again, cobalt creep is the largest here. Why? Because it's my smallest grain size. So if we're assuming grain size strengthening, it means that my DG of 5 is less than my DG of 4 is less than my DG of 3 is less than my DG of 2. So 5, 4, and then this is my gonna be 3. This is gonna be my 2. So label all the regions. Justified our answers here. Which region will dominate at higher temperatures? We explained that. It must be basically Nabarro herring. Why? Because even though Nabarro herring, if we look at our grain sizes, even though we know that my diffusivity in the grain boundary, my GB, is going to be greater than the diffusivity in my bulk, we're looking at our total strain rate in our material. So I have much more bulk, essentially. I didn't change my. I have much more bulk that can contribute to the strain of my material than my grain boundary. So even though I'm faster than the grain boundary, I don't have enough. Now that changes is obviously if I completely, shrink that grain size. So we kind of answered that. Higher stresses, we saw the scaling relationship. Power law creep, it's sigma to the 4 to the 6 power. That's a huge power law scaling. If the material is annealed at low temperatures for short times, which region will dominate? Well, if it's annealed at low regions, short times, then your cobalt creep, again, you're going to have small grain size, so if I have a material with super small grain size, my cobalt creep region will dominate. Okay, turns out these alloys are extremely versatile. They can be solute strengthened, cold worked, grain size strengthened. Write out the scaling relationships for each of these mechanisms. So for my cold worked, I know that my sigma y scales as basically my dislocation density to the 1/2. For my solute strengthened, my sigma y scales as the concentration of the solute to the 1/2. For my basically grain size, or my Hall Petch, essentially, we have this relationship, sigma y scales as d to the minus 1 power. And we can actually go dg to the minus 1. Yep. And then finally, for the precipitate strengthening, we have this kind of cutting and bowing relationship. So, got that. What happens to the yield strength for a material grain size less than 10 nanometers? So if I have a super small grain size, I can only fit basically about 1 dislocation in it. So I don't get this, like in larger grain size, this dislocation pileup mechanism. So you actually see for Hall Petch relationships that your yield strength as a function of dg, it is going to kind of increase, and then as grain size decreases, and then it's going to kind of fall off. So those are hard materials to make. You're usually about 10 nanometers or less. Those are very small crystal, super small grain sizes. So it will decrease for grain size less than 10 nanometers. If I anneal material at long times and high temperatures, what strengthening mechanisms are affected? So this mechanism will be affected, and Hall Petch will absolutely be affected as well. Because again, I will decrease the number of my dislocation, or my density of dislocations, and I'll also I'll increase my grain size dg, so that both of these will essentially decrease my yield strength. Finally, looking at the basically cutting and bowing below. So again, for this system, I have these precipitate particles with different radii. So I know I have 2 different energy penalties and mechanisms. So as my dislocation line kind of interacts and moves through these, it could either cut that dislocation in half, which creates a surface area, or it may be forced to essentially like bow, to kind of bow around this dislocation. So I don't want to cut large particle sizes. So when my radius is very large, I don't want to cut here because I'm creating a lot of surface area. So I want to cut small particles because small particles have my curvature, kappa is equal to 1/r. Small particles have high curvature, bowing around something that's high curvature. Instead, I want to kind of bow here. Fantastic. So we have the energy penalties. How will this curve change if the volume fraction of the precipitates decreases? So if my volume fraction decreases, I'll have less particles to cut. So actually, basically, this radius may move further to the right. So I may be cutting more because I'm creating less surface area. Excellent. So now on to question 4, and then that is the end of our exam 2 prep. See you next video. Thanks. Bye.